What's going on, guys? So this is my A-level physics revision video on the entire wave topic. So everything you need to know about waves will be in this video. This video applies to those of you taking A-level physics in AQA, EdXL, OCRA, OCRB and EDUCAS. There is a small variation between them, the different exam boards, but the majority of the physics is constant across them all. So the reason why I made this video is because I know that a lot of kids struggle with this topic. There's loads of little bits there and they're very hard to get your head around, so hopefully I've broken it all down for you. You should be using this video if you're going to revise for, let's say you have an upcoming test in waves, or you're going to do your end of year exams in year 12, or if you're revising for your actual A-levels and you're in year 13, and obviously you want to gain the maximum highest grade possible. If you don't know who I am, my name is Mr. Ceerazzledazzle. I'm a qualified physics teacher with over 15 years teaching experience. And in my spare time, I've been tutoring and I've been helping loads of kids improve their grades. But the main thing I do is I make educational content on my YouTube channel. And obviously all the content is free to use, so therefore you can teach yourself the entire course. Right, and obviously if you don't understand something, or you're a bit unsure about something, or if you spot any problems, just comment on the video and I'll do my best to respond to every single comment. And as you can see, we can be able to learn together, and obviously everyone improves their physics. All right, we'll make a start in 3, 2, 1, let's go. A-level physics waves. Right, there are two types of waves, transverse waves and longitudinal waves. In transverse wave, the oscillations are perpendicular to the direction of energy transfer. Longitudinal wave, the oscillations are parallel to the direction of energy transfer. Transverse wave, so here is a picture of a transverse wave. It goes up and down. The distance from one point to the next identical point is called the wavelength. So in this diagram I've drawn it from peak to peak, but it's the same distance from trough to trough, or from there to the next cycle, there to there. That's all the wavelength. The amplitude is the distance from the central rest position to the peak over here. That is the amplitude. The link between amplitude and loudness. So the loudness of a sound wave is related to the amplitude. We can see that we have two waves over here. The greater the amplitude, the louder the sound will be. So as you can see, the frequency is constant here, but this sound on the right is going to be louder because it has a higher amplitude. Longitudinal waves. So longitudinal waves over here, I've drawn it. So imagine I have a slinky spring, and each one of these lines is one of the slinky springs. If you were to shove the slinky spring across, what happens is they will get bunched up at certain points, and they will be further away at certain points as well. The points where they're completely bunched up, the central position, this is called a compression. The points where they're furthest away from each other, it's called a rarefaction. Now, the wavelength for a longitudinal wave is the distance from compression, the central part of the compression, to the next central part of the compression. So that is the wavelength over here, or the difference between the distance between the rarefaction to the next rarefaction. This is going to be the wavelength over here. So make sure that you're happy with that for the longitudinal wave. Sound waves. So sound waves, we've got, this is a good example of a longitudinal wave. We have on one side we've got a speaker, the opposite side we've got you. First of all, this is undisturbed air. So obviously when sound waves are produced, it causes the air to vibrate, and obviously compressions are formed and rarefactions are formed here because sound is a longitudinal wave. And obviously the distance between one compression to the next compression is called the wavelength. The superposition of waves, right? Two waves can be added, so if they arrive at the same time, two waves can be added and be doubled up over here. So I've always drawn it in terms of an A and B here. So let's say we have these two waves. Let's say they are traveling, and if they were to meet at the correct point, they could double up to make a super wave if you want. I always talk about it in terms of superposition, super wave is made. So the amplitude of the first wave is A, the amplitude of the second wave is B. The total amount will be A and B because they will arrive in phase and they will double up here. So look, the frequency remains the same, but the amplitude is much larger now. So this is going to be the superposition of waves. So the fact that you can add two waves together is called the superposition of waves. And obviously, what happens if they are arriving in antiphase here? So this wave, let's say we were to add these two together, what would happen? Well, obviously this peak will cancel out with this trough, and obviously this trough will cancel out with this peak. So these two waves, when they add, they cancel each other out. So if two waves arrive in antiphase with each other, they will superimpose and they will cancel each other out. There is no resultant wave in this case. Now, the phase angle of a wave. So in order to understand this, I always draw a circle. So in maths, hopefully you recognize that 0 degrees is here, going all the way around is 360 degrees. This is like a wave because it goes up, down, and to the center. There are 4 different points. 1, 2, 3, 4. 1, 2, 3, 4. So a wave can be thought of as a cycle or a circle here. And now we can talk about different parts of the wave in terms of its degrees. So we know that 0 is here and going all the way around is 360. So initially 0 is here, all the way around is 360, the same idea. But in physics, we don't use angles in terms of degrees. We try and use radians over here. So make sure you can convert from degrees to radians. So we're going to say 360 degrees is 2 pi radians. So those are the units from now on. So obviously, if I have 0 degrees, it's 0 radians. If I have 360 degrees, it's 2 pi. 180 degrees is now pi, because 2 pi, if I was to divide it by 2, makes pi. And obviously 90 will be pi over 2, and 270 degrees makes it 3 pi over 2. If you want to calculate degrees, you want to convert from degrees to radians, you times by 2 pi divided by 360. So you times by 2 pi divided by 360 here. And if you want to go from radians to degrees, you times by 360 divided by 2 pi. Phase difference, right? So when we talk about waves, we can also talk about the difference in phase between two waves. So if I have this wave A and this wave B over here, we can see that they are doing the same thing at the same time, at all times here. So look, we've got 0 to 2 pi, and look, this one for B is also doing 0 to 2 pi, and they're doing the exact same thing. So is there a difference in phase between these two waves? No, because they're doing the exact same thing at the same time. So you can say that the phase difference between these two waves is 0 or 2 pi. Don't forget, it can be 2 pi because the whole wave can be shifted to another 2 pi here. So in this case, at the top, if their waves are in phase, they have a phase difference of 0 or 2 pi, or it could be 4 pi as well. So 0, 2 pi, 4 pi, any multiple of 2 pi as well. Then the one at the bottom, let's look at this one. Let's say I have A over here and B over here. What is the phase difference between these two waves? Well, look, this one, it's going up 4 pi, and this one is going down. Well, obviously, if I was to shift this one by pi, the first wave, it would move over to here. So this hump would move over to there, and obviously this one will fill in the gap here. So now the phase difference between these two waves is pi. And if therefore we can say that if the phase difference is pi or 180 degrees, they're going to be in antiphase to each other. So they're going to be in antiphase to each other. So the top one is in phase because they have a phase difference of 0 or 2 pi, and the bottom one is going to be in antiphase because they have a phase difference of pi or 180 degrees. And this one over here, I've just drawn this one's going to be a phase difference of pi over 2. Yes, so this one's going to be a phase difference of pi over 2 because, look, this one, if you were to think about this B one over here, it's going down. So look, it must have been shifted by pi over 2 to look like this. Path difference. Now, path difference is a concept which loads of kids get confused about. I'll quickly run it through here. Let's say we have a point A and a point X and point B and point X. The difference between the two paths is simply the path difference. The name's on the tin. So let's say this is 20 meters and this is 15 meters. The path difference is going to be 20 minus 15, which is going to be 5 meters. So 20 minus 15, the path difference is 5 meters. Now, this is really important because it can tell you what will happen if two waves meet at this point. The path difference will tell you if two waves will arrive in phase or in antiphase. So look, let's say A releases a wave. Yes, it's traveling outwards over here. And B releases a wave as well. It's traveling outwards over here towards point X. Well, we can determine if it arrives in phase or in antiphase based upon the path difference. So it's all about the path difference, which I'll explain in a minute over here. So the path difference will help us to determine if waves arrive in phase or in antiphase. Path difference. Right, so how to determine if waves arrive in phase or out of phase based upon the path difference. So first of all, you find out the path difference of two waves to a certain point. If the path difference is a whole number of wavelengths, n lambda, the waves will arrive in phase, and due to superposition, constructive interference will occur and they will double up. So look over here, A and B. Right now it's 60 minus 40, which is 20 meters. But if the wavelength is 10 meters, you can see that's a whole number of the wavelength, 2 lambda. So when the path difference is 20 meters, it's 2 lambda, 2 whole wavelengths, therefore they arrive in phase. What happens if the path difference is n plus a half lambda? Right, so if the path difference is half a wavelength, or 1.5 a wavelength, or 2.5 the wavelength, the waves will arrive in antiphase, and due to superposition, they will cancel out and destructive interference occurs. So we can see over here, A and B, the path difference is 60 minus 35, yes, which is going to be 25 meters. But if the wavelength is 10, that's obviously 2.5 wavelengths. And you can clearly see that, look, they will cancel each other out because the trough of this one is going to be colliding with the peak of another one. Therefore, the resultant wave is 0. So to summarize, if the path difference is n plus a half or lambda, therefore it will arrive in antiphase and cancel out. Standing waves or stationary waves. So let's say we have two waves traveling in opposite directions to each other. And as they move through each other, what will happen is they will line up at certain points and they will cancel out certain points. And then as they keep on moving, there will be a cycle alternating between doubling up and cancelling out. First of all, the two waves have to be coherent, which simply means they need to have the same frequency and wavelength, and they need to have a constant phase difference between them. Right, so over here I've drawn both the waves, the red wave and the blue wave, and as you can see, when they both line up, they double up. So these two waves are in phase with each other, hence why the resultant wave that you see is going to be twice the amplitude over here in each case. But as they continue to move past each other, then the peak of one hits the trough of the other one, they will cancel out. And then it continues to move again. We can see that, yes, it will be the reverse of the original, going down instead, but double the amplitude. And then it keeps on going on this cycle. So it goes to doubling up, cancelling out, doubling up in the opposite direction, then cancelling out over here. So overall, you end up seeing wonderful patterns like this. So this is all of them. Let's say it's going to be, obviously this is when t is equal to 0. Then over here, it's the time period for one oscillation. Then obviously halfway will be looking like this. It's the inverse of the first one. But it goes to 0 each time. So 0 in between. So there to 0 to there to 0 to over here. So obviously, what would you see in like a split second? Obviously, you'd have a blend of all of them. So they usually draw it like this. They have one bold line to show you what it looks like. And then they have the dashed line to show you what it becomes halfway through its cycle, looking like this. And this is the resultant wave that you will be able to see, obviously, when you look at the standing waves. Then, to talk about different parts of a standing wave, first of all, there are points called nodes and antinodes. Nodes are points of no displacement. These are points of no displacement. Antinodes are points of maximum displacement. So the particles have been maximally displaced from their equilibrium position over here. Think of the word banana over here. You can simply see that every A is separated by an N, and every N is separated by an A as well over here. Fundamental frequency and harmonics for two fixed ends. So let's say we have a string attached on both sides over here, and we set up a standing wave. So we flick it, and obviously it goes from the top to the middle to the bottom to the middle to the top again. F0, we're going to call it the fundamental frequency, and obviously it's called the first harmonic here. Basically one loop. If I were to double this frequency, yes, over here, we'd end up with two loops. That's what you'd see, and obviously you can see it alternate. So this one will go down to the middle, bottom, then arrive back, and this one's doing the opposite thing at the same time. This is the second harmonic, triple the frequency, third harmonic, quad the frequency, will be the fourth harmonic over here. So one all the way across here, we end up with these wonderful patterns being observed. Now, what is the link between the length of the string and the wavelength? Right, so loads of kids don't understand this, but all you simply do is this. Just ignore the dash one underneath. Look at the top one over here. How much of a wavelength is this? Well, it's going up and back down to the equilibrium position, which is obviously half a wavelength because a full wave goes up and down back to the center. So this is going to be, the length of this is equal to lambda over 2. So that's going to be lambda over 2. For this wave, for the second harmonic, we can clearly see that it's going, this is one complete wavelength. Just looking at this one. This one, the third one, it's 1.5. So L is equal to 3 lambda over 2. This one, it's going to be, this length of the string is equal to 2 lambda. And therefore the general relationship L is equal to n lambda divided by 2, where n is the number of harmonics. Fundamental frequency and harmonics for pipes with two open ends. Right, so let's say right now we have a pipe, both ends are open. Both ends are open, yes, not just one of them, both ends are open. What will happen is an antinode will be set up at the ends because the particles can rush in and out, and node in between. So this is the first harmonic, this is what you will see. Second harmonic, yes. Third harmonic, and the fourth harmonic in this one. You keep adding loops each time. So look, we've added one loop there, we added 2, and there are 3 loops in this one. This is obviously F0, 2F0, 3F0, 4F0 over here, and these are all the harmonics. Then, what is the link now between the length of this tube and the wavelength? How would you work out the wavelength? Well, don't forget this is one antinode to the next antinode, or you can just simply look at the bold line. How much of a wavelength is that? Well, that is going to be half a wavelength. Don't forget, it needs to go all the way down, and this one has to go up to make it a complete wavelength, so this is going to be half. So L is equal to lambda over 2 for this one, for the original, for fundamental frequency. This one, L is equal to lambda. This one, it's equal to 3 lambda over 2. And this one, it's equal to 2 lambda. So look, we can see that, watch carefully for this one. So it's going to be half plus a half plus a half. So it's 1.5 plus a quarter, and the quarter makes it 2 lambda. So in this one, it still obeys the same pattern. L is equal to n lambda over 2. Similar to the one which we had where both the ends were fixed, not moving. Then the last one for harmonics for a open-ended tube and a closed-end tube over here. So at the end, it's going to be an antinode. And the point where it hits the end of the box, don't forget the particles can't move here, hence why it's a node. So this is the first harmonic. Then if I was to, with F0, double F0, it looks like this. Triple F0. And 4 times F0, it looks like this one. So just adding the loops each time. Yes, a nice simple pattern. Now, being able to link the length of the open-closed pipe to the wavelength of the standing wave. Right, so now if we were to look at the length of the tube and how we can link it to the wavelength, well, the first one, look carefully, look at the bold line, that's only a quarter. L is equal to lambda over 4. This one, L is equal to 3 lambda over 4. 3 lambda over 4, because look, it's 3/4 of a wavelength. This one, it's 1 1/4, which is 5 over 4. So the general pattern will obey L is equal to n lambda over 4, where n is 1, 3, or 5. So look carefully, 1, 3, 5, obviously 7, and keep going onwards. Frequency, tension, and mass per unit length of a standing wave on a string. Right, so let's say we have this wave on a string, yes, fixed, yes, we recognize L is equal to n lambda n over 2, yes, depending on the number of harmonics you've got. But obviously we recognize that lambda n is also 2L over n, yes, twice the length divided by n, if I was to rearrange that here. The speed of the wave is equal to the frequency times by lambda n. Frequency is equal to v over lambda. And we also know that the frequency is equal to v divided by 2L over n. 2L over n, we just replace lambda, yes, from this one over here. Therefore, the frequency is equal to nv over 2L. Now, the velocity of the wave will be related to the tension in that string, the tension in the string that's moving, divided by the mass per unit length. So if you were to measure the mass of that rope, yes, divided by the length of the rope, that will give us the quantity mu, which is going to be m over L, that one over there. So now if I was to plug that into this equation, f of n is equal to n root t over mu divided by 2L. Therefore, it pops out becoming n divided by 2L root t over mu. So this is the frequency for n harmonics, whichever one you're looking at. So for the first one, f will be equal to 1 over 2L root t over mu. Just make sure you're happy with that. So whichever frequency you're looking at here. The double slit experiment, or two-source interference. Right, so over here we've got a monochromatic light source. That simply means a light source giving out only one wavelength of light, and it's going to travel through here and hit 2 slits. Right, what happens is, as it travels through, diffraction occurs for the first slit, and diffraction occurs across the second slit. Then when they hit a screen, what will happen is you will see these bright spots and spots where there's no light. Yes, sorry, bright spots and nothing in between. So over here. Now we're going to talk about a couple of things. A is the distance between the center of 2 slits. D is the distance between the slits and the back wall over here. Y is going to be the fringe separation, the distance between each of the bright fringes. Okay, so first of all, you end up with the following relationship. Lambda is equal to AY divided by D, where A is the slit separation, D is the distance between them, and Y is the fringe separation. Right, why do we get these bright spots? It's because obviously it's due to the path difference the waves will travel from the first slit and the second slit. Obviously, they must be arriving in phase here because the path difference must be a whole number of wavelengths. And obviously, if there is nothing being observed here, the path difference must be n plus a half wavelength because they're cancelling each other out, which we just said from previously in the superposition topic of waves. So what you observe is the bright spots, and therefore we call this constructive interference, and where they cancel out, that will be points of destructive interference. The reason why this experiment is really important is because it shows us that light can behave as a wave, because diffraction is only a property of waves. So if you're asked about describing an experiment in which light behaves as a wave, this is definitely one to refer to. And here are some two diagrams showing you that the diffraction pattern is occurring as it enters both the slits. We end up with these wonderful patterns over here, and this one over here. Look, the light enters, and look, diffraction occurs, and points where they double up over here and where they cancel out in between. And obviously Y is the separation between the bright fringes over here. Diffraction. Diffraction is simply going to be the spreading of waves as they meet an obstacle or a gap. Over here we've got some wave fronts, and as they enter the gap we see diffraction occurs over here. The wavelength is the distance from one wave front to the next. S is the slit separation. You can clearly see this one, it hasn't got a great amount of diffraction. There's points there and there where there's no diffraction, well, it hasn't reached us, yes? So like these points you wouldn't feel the wave, but in order to get maximum diffraction you need to have that the wavelength must be greater or equal to the slit separation. So the maximum diffraction is when the wavelength is greater or equal to the slit separation. Diffraction gratings, right, so rather than just having two slits, we can have many slits now. So diffraction gratings are simply when there's got loads and loads of slits, many lines per meter. So now, over here we can see that we've got here the slits now. So let's say we've got loads of them, yes, within a small unit of area. Lowercase d stands for the slit separation. They usually give you the value of n, which is the number of lines per meter. So they might say to you, I've got 300 lines per meter, and therefore you've got to calculate the slit separation between them. So in order to do that, the slit separation is equal to 1 over n, where n is the number of lines per meter. Make sure you've actually converted it into number of lines per meter, yes? Sometimes they give it to you in number of lines per millimeter. So now, as you can see, we've got monochromatic light source, it hits a diffraction grating, and we get this wonderful patterns being observed. So now look, it's more spread out compared to the double slit experiment. So obviously they still get the same maximas and the same minimas, obviously because of constructive interference and destructive interference over here. There's a central maxima right bang in the center, obviously in front, perpendicular to the slits over here, right in front of it. Right, diffraction grating formula derivation. So here's the derivation if you want to know where it comes from. So let's say we've got slit 1 over here, S1, and slit 2, S2. We have a line drawn towards it to the first maxima, not the central one, but over here, either side of it, and from S2 to over there. Well, obviously the extra distance, if I drop this triangle down, and we can make a triangle over here, this is this triangle blown up over here, we can see that S1 to S2, that distance is D, and then the extra distance, obviously, because it must have travelled a whole wavelength more, because here the path difference is 0 because they've travelled equal distance. So this one must be one complete wavelength, n lambda over here. So therefore we can say that S2p, that this distance, minus S1p is equal to n lambda, a whole number of wavelengths. Now from here we can actually talk about the angle between the central maxima and the first maxima adjacent to it, yes, over here. Now if I drop this line across, this value of theta is the same as this value of theta, this one over here, this one right here. So these two values of theta are the same because these two triangles are similar to each other. You can pause the video and check yourself, both these triangles are the same. Therefore, we can link them all together, that if we were to find sine of this angle theta is opposite, yes, n lambda divided by d. So therefore, rearranging it then, d sine of the angle theta n is equal to n lambda. Over here, where n is the order number. So for the first order, for this one, yes, over here, so the first one, n is 1. For the second one, n is 2. For the third one, n is 3. So therefore, d sine theta n is equal to n lambda. And there we go. Theta n is obviously the angle at which the maxima is observed for the order n. And lambda is the wavelength of light. Refraction. Refraction is the change in direction of a wave as it enters a new medium due to a change in its velocity. If I'm going from less dense to more dense, the relative velocity of the light decreases, the light bends towards a normal and the wavelength decreases. If I go from more dense to less dense, the relative velocity of the light will increase and the light bends away from the normal and the wavelength increases. Make sure that you're happy with that upon entry, and upon exit you can draw the ray diagrams. Now, wavefronts instead. So if you're looking at the wavefronts right now, you can see that, look, the wavelengths get closer together over here. And this one, as it goes to a less dense medium, they get spread out. So the one thing that remains the same at both points upon entry, upon exit, is the frequency. So the number of waves exiting this medium must be equal to the number of waves per second entering this medium. So both the frequencies must be the same. So F1 is equal to F2, and therefore V1 over lambda 1 is equal to V2 over lambda 2, because wave speed is equal to frequency times by the wavelength. Now, the refractive index of a material. The refractive index of a material is simply a measure of the amount of refraction that takes place within a material. The greater the refractive index of a material, the greater the amount of refraction. The refractive index is equal to the velocity of light in a vacuum divided by the velocity of light within the material itself. N is equal to C over V. It has no units because you're dividing meters per second by meters per second. Over here I have a table which just goes through the refractive indexes. Diamond has one of the largest, yes, and the vacuum has a refractive index of 1 because it's the speed of light in a vacuum divided by speed of light in a vacuum, which makes 1 exactly. Snell's law. Snell's law simply relates the refractive index of the first medium and the refractive index of the second medium together, along with the angles from the normal. So they can be related by n1 sine of the angle theta 1 is equal to n2 sine of the angle theta 2, where n1 is the refractive index of the first material, n2 is the refractive index of the second material over here. And obviously in this diagram, n2 is greater than n1 because it's bending towards a normal. The critical angle. The critical angle is the angle of incidence at which the angle of refraction is 90 degrees. Beyond the critical angle, total internal reflection occurs. This only occurs if n1 is greater than n2. That means that the refractive index of the first medium is going to be greater than the refractive index of the second medium. So you're going from more dense to less dense. So over here we've got 3 diagrams, 1, 2, 3. As you can see that theta 1 is less than the critical angle, so refraction occurs. So yes, this is theta 1 is less than C. Then if we keep increasing theta 1, there's a point, then this angle C is called the critical angle, at which the angle of refraction, can you see, it will be 90 degrees. It goes along the boundary over here. And then beyond the critical angle, so any value greater than the critical angle, the ray of light will be totally internally reflected within the medium itself. Right, now we're going to derive a formula relating the refractive index of the first material and the critical angle. So in this example, theta 1 is equal to C, and the theta 2 is 90 degrees. Now, n1 sine theta 1 is equal to n2 sine theta 2. Therefore, the refractive index of glass is equal times by sine C, sine of this angle C, is equal to the refractive index of air times by sine 90 over here. Sine 90 is 1, so therefore this becomes refractive index of glass times by sine C is equal to 1. Don't forget the refractive index of air is approximately equal to 1 as well. Therefore, rearranging this, the refractive index of glass is equal to 1 over sine C. So make sure you can be able to derive that yourself. Color of light and refraction. Red, orange, yellow, green, blue, indigo and violet. This is the visible light spectrum. Richard of York gave battle in vain. As you can see that we have the wavelength decreasing and the frequency increasing. If we have a rectangular glass block, we shine a ray of light into it. If we change the color, we get different amounts of refraction occurring based upon the wavelength. Right, so as you can see, what's actually happening is as the wavelength increases, yes, what actually happens is the relative velocity within that material must increase because the frequency remains the same. And what is the impact of that on the refractive index? Well, if the relative velocity within that medium goes up, then the refractive index of that material goes down, depending upon that ray of wavelength here that you're using. So just making sure that you're happy that the refractive index of the glass with red light is less than the refractive index of the glass with blue light incident upon it due to this principle. Lenses. So there are 2 types of lenses, converging lenses and diverging lenses. You can have the symbol for the converging lens, the arrows are pointing away from the line. Diverging lens, the arrows are pointing inwards. So when parallel rays of light enter the converging lens, they focus towards a point. This is called the focal point. Over here, the distance between the lens and the focal point is called the focal length. Then if we have a diverging lens, we can see that the rays of light, they move off at an angle and the focal point is on the same side of the lens over here, so you have to extrapolate them backwards with some dashed lines. So this is going to be a virtual focal point over here with a virtual focal length as well. The power of a lens. The power of a lens can be determined by the focal length over here. So as you can see, the focal length is the distance from the lens to that point. The power of the lens is 1 over f, measured in diopters. Yes, there we go over here. So 1 over f, so that's going to be 1 over meter is a diopter over here. To combine powers of lenses, you simply add them together. So if you have 3 lenses, you simply add all the powers together to make the total power. Lenses and the eye. So let's say we have someone's eye over here. 20/20 vision means that the rays of light enter the lens and they focus towards the back of the retina. But if you are short-sighted, they converge too early. So therefore you need a diverging lens to spread them out, therefore they hit at the correct point at the back of the retina. If you're long-sighted, the rays of light converge too far beyond the retina over here, too far away. So therefore you need a converging lens to make them converge earlier, hence hitting at the correct point. So therefore, if you are short-sighted, you have a diverging lens for your glasses, and if you are long-sighted, you have a converging lens in front for your glasses. Now, drawing ray diagrams. So first of all, here is the principal axis and here is the converging lens. If you have an object over here in red, the image is formed on the opposite side of the lens. So you always draw a ray of light from the top of the object through the center of the lens with no refraction occurring, then one going horizontally across, then through the focal point. Where these two meet, that's where the virtual image is formed. Now, the image is going to be diminished, inverted, and real because it's smaller. So the location of the object will determine the properties of the image here. So as I move this into different points, we'll get different properties of the image being formed. Now, if the object is in between 2F and F, we do the same thing again, one ray of light going across, then one going horizontally, then through the focal point. Then we can see that the image is much larger than previously stated. So over here it was small when the object was greater than 2F. Now if the object is in between 2F and F, don't forget F is the focal point. This is twice the focal, F is the focal length. 2F is twice the focal length, so it's in between here. The magnification is going to be the image height divided by the object height, so I over O. Now this one will be magnified, inverted because it's upside down compared to the object, and it's a real image because it's formed from real rays of light. Then if we put the object in between F and the lens, now the image is not formed on the opposite side of the lens, it's formed on the same side as the object. So now the ray of light goes from the top of the object through the center, then one goes across, then through F. These two rays will never meet, but if we extrapolate the lines backwards, we'll see that they both converge to a point at the top, and this is where the image is formed. Notice it is now upright. Yes, it's a virtual image, and it's now magnified. And this is going to be how a magnifying glass works, because don't forget, you take a magnifying glass, you put an object in front, on the other side, and the image is formed on that same side as well. For our diverging lens, as you can see, that's the arrows have changed for the lens over here in the center. We still take a ray of light going through the center of the lens with no refraction, one going across, but this one at an angle. Don't forget it lines up with the focal point, so this ray will line up with the focal point. We extrapolate this line backwards, where these two lines meet, that's where the image is formed over here. So notice it will be upright, it will be virtual, and it will be diminished because it's smaller. The thin lens equation. Now there's an equation which relates the focal length, the object distance, and the image height all together. It's going to be this. So first of all, we're going to call U the distance between the object and the lens, and V the distance between the image and the lens here. 1 over F is equal to 1 over U plus 1 over V. And obviously to fit all possible scenarios, we have a simple convention, one in which real is positive. So if the image is real, therefore you take that as positive. So for converging lenses, the focal lengths are all positive. For diverging lenses, the focal lengths are all negative. Real images and objects have positive distances, and virtual images have negative distances. So make sure that you're happy with all of that. And that's the reason why if you have short-sighted, yes, you have diverging lenses, they are negative values. Think about when you go for an eye test, you can actually ask them, you'll see there'll be minus. If you're short-sighted, why? Because obviously we take it that they are negative because it's a diverging lens. Polarization. So right now light is unpolarized, traveling in multiple planes. Yes, so right now, but if you were to have a polarizing filter, it simply sets the light to oscillate in one plane only over here. And then if you were to obviously put two filters, but one at 90 degrees to each other, the rays of light have now passed through, they get polarized in one plane, but if you put them at another angle, obviously no light passes through here. So polarization is simply when you set the light to oscillate in one plane only. This can also be observed in microwaves, in which microwaves can come out in one plane only, but instead of having a polarizing filter, you can have a metal grill and you have a receiver on the opposite side. The emitter and the receiver are already plane polarized. So when you rotate the grill 90 degrees, what happens is the signal drops down. It drops down to 0 over here. The reason why is because the waves can no longer pass through because it's in the wrong plane. And that's it, everyone, for the entire waves chapter for A-level physics. I hope this video has been helpful to you. I hope it's been enjoyable, and hopefully it's clarified some concepts, and I've hopefully explained it in a nice way that it all makes sense to you now. If you don't understand something, you know, every single comment that's left on the video, I respond to. You can just check it right now. Every single comment I respond to. I'll clarify any misconceptions that you have, and I'll be able to support you if I can actually explain it in a bit more detail. If you're looking for content or you're looking for a breakdown of some of the concepts, you can actually click on my YouTube channel, and I've got in-depth structured bite-sized videos to help you with your studies. Because obviously this is a revision video, I've tried to put it all in a condensed format, but I've got in-depth explanations for every single topic. That's all on my YouTube channel. Just click on the link below and it will take you to it. And as always, guys, give me a like, thumbs up, subscribe, you know, share it with anyone who you think is struggling in physics, and hopefully we can all help everyone obtain the highest grade possible in A-level physics. And ciao, ciao, and goodbye. Oh, and also if you want more content, on my website, there's going to be a revision and notes coming out. All of these notes I've made myself. I haven't actually copied and pasted it. I've made every single thing here. So all of this will be available. Hopefully it'll be a book. If you're also looking for academic tuition, get in contact via the website link above. Take care, guys. Ciao, ciao, and goodbye.
If you're looking for additional resources, including my own revision notes or academic tuition, get in contact via my website or drop me a comment.